So, welcome to the lecture series on mathematical methods and applications. So, in the last lecture we have seen what Fourier integrals are and how we can if we have a Fourier series of a periodic function, how we can represent a non-periodic function from minus infinity to plus infinity by the Fourier integral, okay, that we have seen in the last class. Now, so we have seen that if we have a function f(x), then the Fourier integral representation of the f(x) will be nothing but 1 upon pi integral 0 to infinity a omega cos omega x plus b omega sin omega x into d omega, and where a omega is given by minus infinity to plus infinity f t cos omega t dt, and b omega is given by minus infinity to plus infinity f t sin omega t into dt. So, that we have seen in the last class that if we have a function f(x), then the Fourier integral representation of function f(x) is given by 1 upon pi integral 0 to infinity a omega cos omega x plus b omega sin omega x dx d omega, where a omega is given by this expression and b omega is given by this expression. Now, let us see Fourier sine and cosine integrals. Okay. Now, it is possible to define Fourier sine and cosine integral representation of function f(x) on a half real line, that is from 0 to infinity, similar to the Fourier sine and cosine series defined on half interval that we have already discussed. If we have a half interval, if in a half interval 0 to L, how we can represent Fourier sine and cosine series? What we did there? Basically, we extend, if you want Fourier sine series, we extend the function assuming the function as an even function, and then we extend the function from minus L to 0 also, and hence we got the function from minus L to plus L and periodic, though that is why we can write its Fourier series, Fourier cosine series expansion. Similarly, for the Fourier sine series, we have already observed that if you want Fourier sine series to, we assume function as an odd function, we take the function as an odd function, or we extend the function as an odd function, okay, from minus L to 0, and in this way we can expand, we can write its Fourier sine series expansion. In the similar way, if we want Fourier sine or cosine integral representation of a function from in the half real line, okay, we similarly assume function to be even function for the Fourier cosine integral representation, and for the Fourier sine integral representation we assume function as an odd function. So, how we will do that, let us see. Now, in this we assume that function is defined for x greater than equal to 0 and function and integral 0 to infinity mod of f(x) dx is convergent or converges, okay, that we assume. Now, how we can find out Fourier cosine integral representation of function? So, we use even extension of f(x) to r in order to obtain the Fourier cosine integral representation of f(x), okay. So, that is, we define another function gx. We define function gx in such that gx is an even function, and which is nothing but an even extension of the function f(x). You see, if we define function like this, which is f(x) when x is greater than equal to 0, and it is f of minus x when x is less than equal to 0, and when we replace x by minus x in gx in this definition, what is the definition here? So, definition here is, you can simply see that gx is nothing but f(x) when x is greater than equal to 0, and it is f of minus x when x is less than equal to 0. So, when you find g of minus x, it is nothing but f of minus x when x minus x is greater than equal to 0, and it is f(x) when minus x is less than equal to 0. So, this is equal to f of minus x when x is less than equal to 0 and f of x when x is greater than equal to 0. So, this is same as this function, okay. So, this is nothing but gx, okay. So, therefore, we extend the function f(x) in such that f(x) is such that gx is an even function. So on the negative side, where function where we don't know the value of the function, we assume that function is f minus x, so that this function become an even function. Now we can write its now gx is an even function, so now we can write its Fourier cosine integral representation. How? Now gt is an even function, okay, here this gt is an even function, this we have already defined here, gt is an even function. Since gt is an even function and cos sine is an odd function, so even into odd is an odd function, so this will be 0, okay. And a omega, we know a omega is defined from minus infinity to plus infinity, okay, and this is an even function, I mean gt is an even function and this is an even function, so even into even is even, so this will be 2 times, okay. So in this way, if we writes its Fourier cosine integral representation, that will be given by fx will be 1 upon pi integral 0 to infinity a omega cos omega x dx, because b omega is 0, okay, and where a omega is given by 2 times 0 to infinity ft cos omega t dt, okay. Now similarly, if you want Fourier sine integral representation of a function which is defined in the half range, I mean from 0 to infinity only, so we extend the function such that the new function gx become an odd function. That means we take gx as fx when x greater than or equal to 0 and minus of f minus x when x is less than or equal to 0. Now here when you take g of minus x, that will be nothing but minus gx, that means gx is an odd function, okay. Now assuming gx is an odd function, because gx is an odd function, so when we take Fourier integral representation of function which is given by this expression 1 upon pi integral 0 to infinity a omega cos omega x plus b omega sin omega x into dx into d omega, where a omega is nothing but minus infinity to plus infinity. Now here a omega is here ft is nothing but gt, okay, gt cos omega t dt, because for the full range minus infinity plus infinity we have gt, and this gt is an odd function, odd into even is and odd function, so this will be 0, and b omega which is given by minus infinity to plus infinity gt sin omega t into dt, so this will be odd into odd is an odd function, so this becomes an multiplication of 2 odd functions, an even function, so this is an even function, so this will be nothing but 2 times 0 to infinity gt into sin omega t dt, and from 0 to infinity gt is nothing but ft, so it will be nothing but 2 times 0 to infinity ft sin omega t into dt. So what will be the Fourier sine integral representation of a function? Fourier sine integral representation of a function will be given by, now this a omega is 0, this term will become 0, okay, that will be nothing but fx equals to 1 upon pi integral 0 to infinity b omega sin omega x d omega, where b omega is given by this expression, okay. So this will be the Fourier sine integral representation of a function fx, so that is given in the next slide. So this will be the Fourier sine integral representation of a function fx. Now again as we did in Fourier integral representation, we assume function is piecewise continuous on interval 0 to L, okay. It is absolutely convergent on the real axis, okay. Function has a left and right hand derivatives at each x belongs to 0 to infinity. So this is the condition which we should assume, so that the function Fourier integral representation exists. Then at a point of continuity of fx, the Fourier cosine and sine integral representations converges to fx at a point of continuity, and at a point of discontinuity it converges to the average of left hand and right hand limit at that point, okay. Now let us solve few problems based on this Fourier sine and cosine integral representation. For this we solve few problems. Now we have to find out the Fourier cosine and sine integral representation of this function e ki power minus kx. X greater than 0 means it is defined on the half range from 0 to infinity, okay. And for the Fourier integral representation we need a function defined from minus infinity plus infinity. So that means if it is half range, there will be either Fourier cosine integral representation or Fourier sine integral representation of the function. If we need Fourier cosine, that means we extend the function fx assuming function as an even function, and if we need Fourier sine integral representation, we extend the function fx assuming function as an odd function, okay. So suppose we need Fourier cosine integral representation. So Fourier cosine integral representation of fx is given by what? Is e ki power minus kx, okay. So we know that Fourier cosine integral representation of function is given by fx equals to 1 upon pi integral 0 to infinity a omega cos omega x into d omega, because for the Fourier cosine integral representation we have only the cosine series and the b omega is 0, okay. So what will be a omega? So let us find a omega. For this, a omega is nothing but 2 times 0 to infinity e ki ft cos omega t dt. So it is 2 times 0 to infinity. What is ft? E ki power minus kt, and it is sin, it is cos omega t dt. So this will be given by 2 times. Now let us integrate it. So you can easily integrate by integration by parts. So this will be nothing but 1 upon k square plus omega square. This will be minus k into e ki power minus kt cos omega t. It is minus e ki power minus kt minus minus plus omega sin omega t, and that will be from 0 to infinity, okay. Now it is nothing but 2 upon k square plus omega square. It is nothing but minus k cos omega t upon e ki power kt plus omega sin omega t upon e ki power kt from 0 to infinity, okay. Now when t tend to infinity, this is a value lying between minus 1 and plus 1, upon infinity will be tending to 0. This is also tending to 0, and when t is 0, it is 1 and it is 0. So this value is nothing but 2k upon k square plus omega square, okay. So therefore the Fourier cosine integral representation of this function e ki power minus kx will be nothing but 1 by pi times integral 0 to infinity, it is 2k upon k square plus omega square cos omega x d omega. So from this we get integral 0 to infinity k cos omega x upon k square omega square d omega will be nothing but pi times, pi by 2 times in fact e ki power minus kx. So substituting different values of k, one can get the values of this integral which is given by this expression. Suppose k is 2. So for k equal to 2, the value of cos omega x upon 4 plus omega square will be given by this 2 will come here, pi by 4 e ki power minus 2 x. So substituting different values of k, we will get different values of this integrals, okay. This integrals can be find out, this I want to say, okay. So this is the Fourier cosine integral representation of this function, is this, okay. Basically cosine integral representation is this of e ki power minus kx. When we simplify this, so from here we can find out different values of substituting different values of k, the value of the integral, okay. Now the Fourier sine integral representation, of the same function, integral representation, okay. So, what is the Fourier sine integral representation? That will be given by 1 upon pi integral 0 to infinity f t fx sine omega x dx d omega, and where b omega, okay, it is b omega, sorry, b omega, because a omega is 0, okay, and b omega is given by 2 times 0 to infinity f t sine omega t into dt. So, that will be nothing but 2, that is integral 0 to infinity. What is f t? F t is e की power minus k t sine omega t into dt. So, this integral will be equal to, again we will integrate by parts. So, this is equals to 1 upon k square plus omega square, this is minus k e की power minus omega minus k t, it is sine omega t, and it is minus e की power minus k t, and it is cos omega t, omega times, and 0 to infinity. Okay. So, that will be nothing but 2 upon k square plus omega square, minus can come out, it is k sine omega t upon e की power k t plus it is omega cos omega t upon e की power k t 0 to infinity. Okay. Now, when you put t equal to infinity, t tend to infinity, so this will tend to 0, this will tend to 0, and when t equal to 0, it is 0 and it will be 1 upon this. So, minus minus plus, so it is 2 omega upon k square omega square. So, what will be the Fourier sine integral representation of this function? The Fourier sine integral representation of this function will be nothing but, we have a function e की power minus kx, okay, which is equal to 1 upon pi times integral 0 to infinity, and b omega is 2 omega upon k square plus omega square, and next is sine omega x d omega. So, this will be the Fourier sine integral representation of this function. Okay. Now, hence find the Fourier cosine integral representation of this function. So, this we have to find using the previous result obtained from the previous problem. Hence, so we have to find Fourier integral representation of this function. So, let us find Fourier integral representation of this function. So, for Fourier integral representation of this function, function is 1 upon 1 plus x square. So, it is given by, function is 1 upon 1 plus x square. So, Fourier cosine integral representation of this will be nothing but, it will be fx will be equals to 1 upon pi times 0 to infinity a omega cos omega x d omega. Now, where a omega is nothing but, a omega is 2 times 0 to infinity f t cos omega t dt. So, this is 2 times 0 to infinity, what is f t? 1 upon 1 plus t square, and it is cos omega t dt. Now, to find out this value, we will use this integral which we obtained from the first part of the problem. Okay. Now, this is cos omega x upon, it will be 1 plus omega square when k equal to 1. So, simply substitute k equal to 1 both the sides. So, when you put k equal to 1, you will directly get the value of this expression, which is 2 into pi by 2 times e की power minus x. So, this is nothing but pi e की power minus x, I mean pi into e की power minus omega. It is a omega function, so it will be omega, this omega. Okay. Because instead of x we have omega, and instead of omega we have t. Okay. That is why here we are having pi into e की power minus omega. So, what is the Fourier integral representation of this function? So, this will be nothing but 1 upon pi times integral 0 to infinity. A omega is nothing but pi into e ki power minus omega and cos omega x d omega. Pi cancels out. So, this will be the Fourier cosine integral representation of this function 1 upon 1 plus x square. So, in this way we can find out Fourier cosine and Fourier sine integral representation of a function. Now, let us try one more problem where we also discuss about discontinuity at a point x equal to 5. Here we have to find out Fourier cosine integral representation of the function. So, we will follow the same methodology which we have discussed here. So, function which is defined here is defined as f(x) is equals to, it is x when x lying between 0 to 5 and it is 0 elsewhere. Okay. So, this is the definition of the function. So, it is defined from 0 to infinity and we want Fourier cosine integral representation of this function. So, for Fourier cosine we need a omega, okay, because b omega is 0. So, a omega is 2 times 0 to infinity f t cos omega t into dt. So, that will be nothing but 2 times, here it is 0 to 5, otherwise it is 0, x cos omega t into dt, which is nothing but 2 times. Now, you can integrate it by parts, so it will be nothing but cos into sine omega t upon omega minus derivative of first integral of second, which is minus cos omega t upon omega square, and it is from 0 to 5. So, this value is nothing but 2 times, when you put t equal to 5, it is nothing but 5 sine 5 omega upon omega minus plus cos 5 omega upon omega square, and when t equal to 0, it is 0, okay, it is nothing but t, yeah, because f(x) is x means f t is t, okay. So, it will be this plus this, when t equal to 0 it is 0, when t equal to this it is 1, so 1 upon omega square, so it is minus is minus 1 upon omega square. So, this will be a omega. So, what will be the Fourier cosine integral representation of this function? So, that will be given by f(x) is equals to 1 upon pi times integral 0 to infinity a omega. A omega is this value, it is 10 sine 5 omega upon omega plus 2 cos 5 omega upon omega square minus 2 upon omega square and whole multiply by it is cos omega x d omega. So, that will be the Fourier cosine integral representation of this function f(x). Now, suppose you put x equal to 5, suppose, so put x equal to 5. So, what will be f5? Since function is discontinuous at x equal to 5, so f5, to find out the value of f at x equal to 5, it will be converges to mean of or the average of value of the function left hand limit and right hand limit at x equal to 5. Okay. So, what is f5 minus? It will be nothing but 5 from the definition. Okay. And what is f5 plus? 5 plus means from right hand side it is 0. So, what will be f5? It will be half of f5 minus plus f5 plus. So, that will be nothing but half of 5 plus 0 is equals to 5 by 2. Okay. So, the left hand side is 5 by 2 and the right hand side is 1 upon pi integral 0 to infinity. When you substitute x equal to 5, okay, it is 10 sine 5 omega upon omega plus 2 cos 5 omega upon omega square minus 2 upon omega square into sine into cos 5 omega d omega. So, if we need this value, suppose this integral from 0 to infinity, so that value is nothing but, you can take pi this side, okay. So, that will be nothing but 5 pi by 2, okay. So, in this way we can find out the value of this expression also, okay. So, now the next problem is Fourier sine integral representation. That also very easy to find out, we can easily simplify and find out the Fourier sine integral representation also. So, again for this problem, for finding sine integral representation, we will find b omega, which is again given by 2 time integral 0 to infinity, it is f t sine omega t dt, okay. So, that will be 2 times, now it is 0 to pi, only defined from 0 to pi, which is given by pi minus t into sine omega t dt. So, that is nothing but 2 times, now you can integrate it very easily, integration by parts. So, pi minus t, it is minus cos omega t upon omega, then minus derivative of this and integral of this from 0 to pi. So, this is nothing but when pi is 0, only when exists when t equal to 0, it is minus minus plus 2 times pi upon omega. So, it is 2 pi upon omega, okay. It is 2 pi upon omega. So, what will be the Fourier sine integral representation of this? So, that will be nothing but f x equals to 1 upon pi integral 0 to infinity b omega into sine omega x d omega. So, that will be the Fourier sine integral representation of this function. So, in this way we can find out Fourier cosine or sine integral representation of a function when defined over the half range by extending the function, assuming the function is an odd function or an even function. So, thank you.